Hey guys, I'm Jade. Today is my LeetCode review one-take vlog on 199th problem. Binary tree right side view. We are given the root of a binary tree. Imagine ourselves standing on the right side of it. We'll return the values of the nodes we can see, ordered from the top to the bottom. And let's see example 1 here to understand this problem easily. We got infinite binary tree here, and the nodes we can see from the right side is 1, 3, 4, and that's our output. Next, let's see example 3 here. We have to handle a bad case. If we got an empty binary tree, our output is an empty list. And then, let's get started with our intuition and main idea to solve the problem. And the first approach that comes to my mind is to do a level order traversal, which is also called breadth first search. We'll process the tree level by level, and we only add the last node from each level to the result list. This is because the last node of each level is the one visible from the right side. So the first approach is breadth first search. And another approach could be depth first search. We prioritize exploring the right subtree first before the left subtree. So the first node we encountered at each depth or level is the rightmost node from that level. Second approach, depth first search. And then let's get started with the first approach, level order traversal. And there are 3 steps. The first step will traverse the binary tree level by level. Second, for each level, we store the last node we encountered. This is node visible from the right side view. And the last step, we'll use a queue or a linked list to maintain the nodes for the breadth first search and iterate through each level. And then let's get started with our code to solve the problem. First, we'll initialize a result list to store the right side view nodes. List of integer, which is the type of each node. And let's call it result. We assign a new empty array list to it. And then we have to handle a bad case. If the tree is empty, we just return an empty list. If root equals null, we just return an empty array list. Then we'll create a queue to perform a level order traversal. And the linked list is the implementation of an abstract queue in Java. Queue of tree node. Let's call it queue. Oops. And we create a new linked list instance to it. New linked list. And then we started this process by adding the root nodes into the queue.offer for the root node. And then we'll create a while loop to start the breadth first search traversal. While not symbol queue.is empty. We'll continue the while loop until the queue got empty. And for each iteration of the while loop, we process all the nodes in the current level. And we'll create an extra variable to keep track of how many nodes are in this level. For example, we'll create an integer variable that's called level size equals queue.size. And then we'll iterate through all the nodes in the current level. We'll create a for loop. Integer I started at 0. When I is less than level size, we'll continue the iteration. And after each iteration, we'll increment the I counter. And for the inner for loop, we'll process each node in the current level. First, we have to get the tree node from the queue. So the code is tree node equals queue.pull. And then we have to check if the node is the last node or not. If so, we'll add it to the result list because this is node or this is the rightmost node from the right side view. If I equals level size minus 1, which means this node is the rightmost node, then we'll add node into the result list with node.value. And for every node, if it has a left child, we have to enqueue it. Similarly, if it has a right child or a right subtree, we also have to enqueue it. And there's one thing we have to remember. We'll enqueue the left subtree first to obey the sequence of pre-order traversal, root, left, and right, so we can process each level's nodes from left to right. And the code is, we have to check if the node .left is not equal to null. If so, we have to enqueue the left subtree queue.offer of node.left. And it's very similar for the right subtree. If node.right is not equal to null, we'll enqueue the right subtree. The code is queue.offer of node.right. And after processing all the levels in this loop, and we just return the result list. As we process all the levels, so the result variable list will contain the rightmost node of each level. And then let's analyze the time and space complexity. So the time complexity, it is big O of n, as we traverse each node for only one time. And for the space complexity, it is also big O of n. And there are two spatial cases. First, if the tree is a balanced tree, we could store up to half of n nodes. So the time complexity for the balanced tree, it is big O of n. And there's, in the worst case, if the tree is skewed, so we could store up to n nodes. So the overall space complexity, it is big O of n. And then let's get started. Let's continue with the second approach, which is depth first search. So for the depth first search, we'll do a pre-order traversal, but we'll visit the right subtree first before the left. This is because in this approach, we can encounter a node at a new level for the first time, and we add it to the result list. And this mechanism could ensure that we can capture the rightmost node first at each level. And then let's get started with our code to solve the problem with the second approach. And first stage is also very similar. We'll initialize a list result to store the rightmost nodes of each level. List of integer. Let's call it list. We'll assign a new array list to it. And then we have to create a helper method will help us to do a depth first traversal. Let's call it DFS. And this method needs three variables. First is the root node. Second is the array list. We have to store each node. And the third parameter could be the depth of the level. And we have to initialize the method with three variables. First is the root node, and then is the result list. And the last one is the current depth, which is 0. And after the recursion, we just return the result list. Then we have to declare and implement the DFS helper function or method. First, we use a private keyword to declare the method with DFS. And the method needs three variables. First is the tree node for this recursion. Second is the result list with list of tree nodes. Let's call it list. And the third one is the depth for this recursion. And inside the DFS helper method, the first step, we also have to check for the bad case. If node equals null, we just return, as there is no more left or right subtrees to process. Second, we have to check if this is the first time to visit this depth. And the condition is if depth equals result list.size. If so, we'll add the current node into the result list. If depth equals list.size, which means this is the first time to visit this level. So we add this node in this recursion into the result list. List add node dot value. Next, we prioritize visiting the right subtree first. This is because we have to make sure the first node we encountered at each depth is the rightmost node. So we have to do the recursion to the right subtree. So the code is DFS of node.right with the list and a new depth, which is depth plus 1. And then we'll do the recursion for the left subtree, DFS of node.left and the result list and the new depth. And that's all the code for the second approach to solve the problem. Let's submit code and check for the correctness. Oops, invalid method declaration. I forgot the void keyword here, sorry. And then let's analyze the time and space complexity. List. Oops, I create a runtime, so I have to fix it. Integer. Then let's analyze time and space complexity. We'll return the list. So the time complexity, it is big O of n, as we visit each node only one time during the depth first search traversal. And for the space complexity, this could be big O of h. Yes, our code got accepted. Big O of n for the time complexity and big O of h for the space complexity, and h stands for the height of the tree node of the binary tree. This is because the recursive callback can go up as steep as the height of the tree. If the tree is a balanced tree, h could be log of n, but in worst case, if the tree is a skewed tree, the space complexity could be big O of n. And that's the end of my LeetCode review vlog on this problem. And I highly recommend you guys to visit my online GitHub page here. You can see all the problem description, an idea, and different approaches with detailed code and final time and space complexity analysis. You can also visit my GitHub repository here, which contains all the code and node to build this online GitHub page. And thank you guys for watching. You can also visit these two websites on my YouTube description below. And thank you guys for watching again. I'll see you next time. Bye bye.